Hi there, welcome to Financial Mathematics. In this lesson, we will introduce a new subject, a new topic. We will indeed introduce the modeling of interest rates. If you remember, I'm sure, until now we have assumed that on the market we had an interest rate, the risk-free, that was constant and given, okay? So it was something that we could even use in order to define a new measure, the risk-neutral measure, that allows us to take care of all the subjectivity on the market and get rid of the subjectivity, so that using the risk-neutral measure, we have this benchmark that we can use in order to assess and price objects on the market. Now, we have seen that the risk-free rate can be negative, can be zero, can be positive, but in any case, it is constant, okay? It does not change over time, not even deterministically, okay? So we are not even saying that it is a function that we completely know, there is no randomness. No, it was just a constant. Okay, what we do now is to introduce a new setting in which interest rates are actually changing over time. They can change in a deterministic way. In that sense, there is no randomness in the way they change, but still they change. And we will see that, for example, we need some adjustments to the things we have seen until now. And we will consider the case in which interest rates are stochastic processes themselves. And for example, one big difference between this new setting and the old setting is that the Cameron-Martin theorem that we have been using until now will need some update. We will have to introduce a more general version, that is the Girsanov theorem. We will see different versions of the Girsanov theorem, and we will use this new machinery to play with interest rate derivatives. That is to say, securities, that is to say, derivatives, whose underlying asset is some sort of interest rate. So we will consider, for example, caps, floors, and other similar objects. But before doing that, we have to introduce some notation of this new setting and also to introduce new measures. So we will see that in the interest rate framework, the physical and the risk-neutral measure are no longer sufficient. We need to introduce some other measures in order to solve some problems that we will immediately encounter. We will take this occasion also to go a little bit deeper into the understanding of what happens when we change a measure, and we will introduce the concept of numeraire in a more formal way. Okay, so let's start with our lesson. Okay, so what we do is the following. We consider a so-called money market account. Now, what is this money market account? It's nothing more than, if you want, a bank account in which you can put your money, and what you get is an interest that essentially represents the actual interest conditions on the markets, okay? Now, the value at time t, for any t from 0 until capital T, that we will call RT, of €1 that we have invested in the money account at time 0 is equal to the quantity e to the power integral between 0 and t of RU du. Now, what is this RU du? And here you already see the difference with respect to the setting we have been considering so far. RU is the interest rate process. Now, if you want, in order to be a little bit more precise, we could write RU omega, okay? Because in principle, this quantity RU can be a part of a stochastic process, okay? So remember that in principle, we can have an omega inside, but to simplify notation in the following, we will omit omega, but we can distinguish different situations. So the simplest one, what we have been doing until now is to assume that RU is equal to a constant R for every U. So at every time instant, I always get the same R. I can have a deterministic function, so RU is a function of U moving in my interval, but in a deterministic way, or more generally, I can have RU omega. Okay, in that setting, I'm in the more general setting in which the interest rate is actually a stochastic process. And we will see that we can have different processes like the Vasicek, like the Cox-Ingersoll-Ross, and so on. Okay, so we will see different possible candidates for these processes. Now, this is the money market account. We will then consider another object, which is a zero coupon bond. So it's a very simple zero coupon bond, and we called PT capital T, so PTT, the price at time T of a €1 zero coupon bond with maturity capital T. So we are considering a bond whose nominal value is €1, so it's a bond that is worth €1 at capital T, and PT capital T is the value at time T of that quantity. So in order to get that value, what do? The price PT capital T is nothing more than the expectation under a measure QR that we will define in a minute. But what I can already tell you is that this measure QR is a measure equivalent to the physical one, okay? And under certain conditions, this measure is nothing more than the risk neutral measure, as we have been calling it until now. But in a more general setting, there are some things we have to take into consideration. So for the moment, we call that just the measure QR. So this price, PT capital T, is equal to the expectation under QR of what? Of the discounting of €1. So imagine that here there is a 1 for €1 at time T with respect to what? With respect to the interest rate process, okay? As I told you before, this quantity here, you have always to think about that as these, okay? So it's very important. That's why, for example, we cannot just take our exponential out of the expectation, because this is something stochastic, okay? So we have to compute our expectation, obviously, once we specify how this R process behaves. And obviously, as usual, we condition with respect to the information at time small t, okay? Now, this quantity PT capital T is very important, and remember, is the price in T of a €1 zero coupon bond with maturity, capital T. Now, if interest rates are deterministic, okay, so if I can just write down my function, but there is no randomness, obviously taking the expectation of a deterministic function is useless, because obviously what I get is the deterministic function itself. So in that situation, I can get rid immediately of the expectation that I can see here, okay? And using the notation that we have introduced for the money market account, we can essentially write that the price in T is equal to E to the power minus the integral T capital T RU du. Okay, so it's the exponential of minus the integral between T and capital T over U du. And this quantity, in terms of the value at time T of my money market account, can be expressed as the ratio of R small t and R capital T. Okay, it's a very simple thing to verify that. If I further assume that my interest rates are not only deterministic, but also constant, we are essentially back to our previous setting, in which the discounting factor was just the quantity exponential of minus R multiplying the distance between capital T and T in terms of time units. Okay, so and we are back to our initial setting. Now, one important concept for us in this new setting is the concept of numeraire. Now, we already considered very heuristically what a numeraire is, and a numeraire is nothing more than any basic standard, any basic unit of count that we can use to express the value of all the different assets, of all the different securities, of all the different objects on a market. Okay, so we decide, for example, that we want to express everything in terms of a given currency. So a currency is a typical type of numeraire. So everything in dollars, everything in pounds, everything in euros. But in the past, we know that people use, for example, salt in order to use salt as a currency. So you can use whatever object, apples, as you see on your screen, whatever you want. Okay, so you can choose the numeraire that you prefer. And what we will see is that it's actually choosing the right numeraire simplifies a lot the treatment of our problems. We will see that until now we have been using, for example, the risk-free as a numeraire. Okay, so we were evaluating everything with respect to the risk-free. We will see that now actually it is more appropriate sometimes to introduce other numeraires. And what we will do is that every time you choose a numeraire, you are implicitly defining a new measure on your market. Okay, so if you use the risk-free rate, we have seen that essentially you play with a risk-neutral measure. If you choose another quantity, you can end up with another measure. We already saw an example. You remember when we were discussing the Wang transform, we have seen the share measure. The share measure is nothing more than the measure equivalent to the physical measure and also equivalent to the risk-neutral measure, in which the numeraire is no longer the risk-free, but it's the stock itself. Okay? What we will do is, for example, to choose as a numeraire the zero coupon bonds and other quantities. And we will see that choosing the right numeraire allows us to simplify extremely the treatment of the different computations that we have to perform. Sometimes something is extremely difficult to be evaluated under the physical measure, it becomes easier to be treated under the risk-neutral measure. Sometimes the risk-neutral measure is not enough and we have to find another measure that allows us to simplify even further. Okay, so we will see all these kind of things together. Now, if we consider our no arbitrage setting, so our setting in which we are assuming that there is no arbitrage, in which we have the two fundamental theorems of asset price and working and all these kind of things, what we have is that the value VT of a portfolio, but more in general, of whatever asset or strategy or security we want to evaluate, so it can be also the value of a derivative that we want to evaluate, the value VT of a derivative at time t, in which the underlying asset follows a process ST, is what? Is nothing more then once we have selected a numeraire, then the expectation with respect to the measure Qn, where that measure Qn is defined through the numeraire. And what we want is that the discounted value with respect to the new numeraire is essentially a martingale. Okay, so this is what we have been doing until now when we were just using the risk-free. What we do in a more generalized setting is to substitute the risk-free with something else. Okay, so what we will try to do is to take the expectation of our asset, of our derivative, with respect to a new measure, which is equivalent to the physical measure, and this measure is the measure Qn, where n is the n that relates to the numeraire nt, which is what we will choose. That can be deterministic, that can be a process, and whatever. We will see that actually we can use processes as numeraire for our purposes. Now, in formal terms, what we say is that once we choose nt, the quantity nt here, okay, what we want is that Vt over nt, so this ratio here, is equal to the expectation under the measure Qn of V capital T and capital T. And obviously, since we want everything to be a martingale, we will have the conditioning with respect to our filtration stopped at time T. Okay, so if you want, in this way, as you see on your screen, we are just restating in very general terms what we said at the very beginning of the course when we were assuming NT to be essentially the risk-free asset. So in which we were modeling everything in a way such that the numeraire was the risk-free asset and so the risk-free rate, okay? Now, if we take the money market account to be the numeraire, what we have is the following. We can always write VT as the expectation under QR of what? Of RT over R capital T, V capital T, and this quantity here is equal to the expectation under QR of what? I can substitute this quantity here. Recall that we have said this before. Okay, remember this. Okay, the only difference is that now we are not necessarily assuming that the process RU is deterministic. So in a sense, since the process RU can be also stochastic, we cannot just get rid of the expectation, okay? So we have to keep everything inside. So what we have is that the value Vt can be expressed as this stochastic discounting factor here, okay? And the value capital T of our derivative of our asset, whatever we want to evaluate. So here you see what happens. The quantity QR is nothing more than the equivalent measure that we define on a market when we use the money market account as a numeraire. Now, if you assume that the money market account pays a constant interest, which is totally constant, in which there is no randomness, we are back to the framework we have been considering, because at that point you can consider the money market account nothing more than a risk-free investment that pays a rate equal to R at any time point. Okay, so there is no randomness. What you do, you just accumulate or discount, depending if you are going forward or backward in time. And what we have is that our measure QR is exactly the risk-neutral measure that we have been playing so far. If the money market account has a behavior which is not as trivial as assuming a constant interest rate, what we will have is that this measure, it's still, we will call that still the risk-neutral measure, but it's a little bit more subtle with respect to what we have seen before. Because now you imagine that obviously if the interest rate itself is a stochastic quantity, then it becomes a little bit trickier to play with these things. Typical, very simple example is what we have just observed, that is to say that I cannot take this quantity simply out of my expectation. I cannot, because what I have is that this quantity here is something stochastic, and possibly, as we will see in a minute, when this quantity here is an interest rate derivative, I have that the interest rate does not only affect the stochastic discounted factor, but is also one of the arguments of these. So there is also dependence among these two elements. So it becomes a rather complicated framework with respect to what we have been considering until now. Now, as I just told you, if I consider an interest rate derivative, in an interest rate derivative, typically the underlying asset that we consider is some sort of interest rate. There are different interest rate derivatives, but if you think of swaptions, if you think of caps, if you think of floors, that we will consider in more details when we want to price them. Okay, in all these different derivatives, what do you have? You have some reference interest rate, or more than one reference interest rate, maybe two, like, for example, when you want to swap the cash flows generated by different interest rates. And then what you do, the value of the derivative necessarily depends on the value of the underlying interest rate. So the interest rate not only enters in the discounting part, as, for example, when we were playing with our European option, American options, barrier options, but is also an argument of the value itself, okay? So as I told you before, the interest rate has an impact on this term, but also on this term. And in fact, it enters here. You see that explicitly in the argument, okay? Now, in the rest of the slides, you will see that I will drop this notation here, in which we have that the value is a time t with respect to the maturity of capital T and the interest rate RT, the interest rate process RT, but this is what we are implicitly saying. So even if we write this, because that simplifies a lot our notation, this is what we are essentially assuming at any time. So you see that the interest rates are an argument of our value function. Okay, that's very important. Now, if you want to model an interest rate derivative, you want to model something in a realistic way. So assuming that the interest rates are constant on the market is not a realistic assumption, but also assuming that they are just deterministic is not a credible assumption. It can be on a very short time horizon, because obviously we will see that interest rates are not as volatile as, for example, prices. The market of interest rates is a special market, as you have also seen in other courses, because, for example, in our system, we have central banks that intervene on the market. They set reference rates. So let's say that you don't see very big oscillations in very short times, apart from very special situations. When you see that, obviously, it is a very big problem for the market. But let's say that in common market periods, interest rates change. We have to model them as something that changes, but at the same time, we do not assume big jumps in the interest rates or very strange behaviors, okay? Yet, we do not assume them to be constant, okay? So if you really want to do something very, very simple, you can assume for a short time horizon something deterministic, but it will not be extremely clever. So the most useful thing that we can do is just to play with stochastic interest rates, okay? And why, for example, can we already say that Girsanov is no longer working? Because you remember that at a certain point, we were playing with a quantity like this that was our Sharpe ratio. Okay, now if the interest rate here is no longer constant but becomes a function, what happens is that also trivially this Sharpe ratio changes. And we know that the Sharpe ratio is one of the drifts we have been playing with when we were moving between Brownian motions and Brownian motion with drift. And so we had to introduce the change of measure to get rid of the drift and blah, blah, blah. In more general sense, we will see that also mu and sigma can change. So automatically everything changes here. And Cameron-Martin is no longer sufficient because of the fact that it only works for constant drifts or with a very slight generalization deterministic drifts. If the drift is not deterministic, because here we have also omega entering, and so we have a stochastic process, then obviously the drift here becomes stochastic, and Cameron-Martin is no longer a viable solution. Now, the point that, as it is written here, the point that the interest rate here appears on the discounting factor and on the value of the asset that we want to evaluate, of the security that we want to evaluate, of the derivative that we want to evaluate, makes everything complicated. Because, for example, if we look at this expectation, we have the expectation of the product of two quantities, of two random quantities. And these random quantities are the discounting factor, so the pink part, and the value of the derivative itself, the green part. Now, one thing that we will see is that trying to model this expectation as it appears on the screen at the moment is problematic. But, for example, if we could assume that this quantity here is independent of this quantity here, the idea is that we could rewrite our expectation as the product of two expectations, okay? obviously also under the conditioning. So let me drop the conditioning. It is there, but just in my very quick notation on screen. So we could write that as two expectations that we multiply in order to get this one. So this one is our big expectation here, and we would like to be able to split, for example, in this way, because that will be much, much better. Now, the point is that we cannot assume that this quantity here is independent from this quantity here, because the interest rate is here and here. But this is where we introduce a new risk measure, because by introducing a new risk measure, what we will see is that we are able to write this expectation in something that resembles this. The only difference will be that we will have two different expectations, an expectation under a first measure and an expectation under another measure, and their product will be equal to this. Okay, so by introducing different measures on the market, we can try to break this joint expectation into the product of expectation. So this is our goal. The measure that we introduce is what you read in the title here, is the so-called T-forward measure. Now, the T-forward measure is nothing more than the measure that we introduce by using as a numeraire the price PT capital T. Okay, so remember that PT capital T is the price in T of a €1 zero coupon bond. Okay, we always take €1 or $1 or whatever you want, because then we don't have to take into consideration the notional principle in general. So if you have a notional principle of 100, you can see that as 100 times €1, or 100 times $1, or 100 times £1. I mean, this is not very important. So what we do is that we choose as a numeraire this quantity here. Okay, so we choose PT capital T as the numeraire. If we do that, we will essentially get this result. This result will be that we can take our big expectation here. This big expectation here is what I've written here in this part. And we can split this big expectation into the product of two expectations. One expectation that will take into consideration the discounting factor, and one expectation that will take into consideration the value of the derivative. And you see that now we can write our expectation of the product as the product of the expectations, as if the quantities were independent, but the trick is not to assume independence, it's just to introduce two different measures that allow us to write this, okay? And actually the way in which we can get this is not very complicated. It's just a matter of playing with the toys we have been playing with until now, and take into consideration this new notation that is meaningful for the sake of actually getting the nice result we are looking for. Now, what we know is that since PT capital T is the price in T of a €1 zero coupon bond, so a bond that has no coupon and that pays 1 at capital T, what we have is that trivially P capital T, so the value in capital T of that zero coupon bond is 1. So you get €1, okay, or $1, whatever currency you want to use, but you get that, okay? Now, if this is the case, what do? We want to introduce the measure QT. Now, according to what we have said before, using the general N notation, we look for a measure, once we have defined our numeraire NT, we look for a measure that satisfies this, such that if I reevaluate the value in small t of my asset with respect to the new numeraire, so I express its value in terms of the numeraire, this is equal to what? It's the expectation under the measure that depends on the numeraire of the value at maturity of the ratio in capital T, obviously, of my derivative is expressed in terms of the numeraire. So if I choose apples, what I'm saying is that the value in small t in terms of apples of my derivative is equal to the expectation under the apple measure of the values in apples of my derivative at maturity once I condition with respect to the information as small t, okay? Now substitute apples with whatever you want, the risk-free, the stock, whatever you want, and you have the general framework. Now, in the t forward measure, what I told you is that our n is nothing more than the quantity pt capital T. So what we do is that we are setting nt here equal to this. This is obviously n capital T. And for the rest, we are just applying what we have written. Now, since p capital T is equal to 1, it simplifies, so we end up with this equality. Okay, so Vt over Pt capital T is equal to the expectation under Qt, this T forward measure of V capital T stopped at Ft. Now, what I can do, I can take this Pt capital T and send it on the other side of the equality. So I'm in this situation. Now, but what is nice is that this value here is what? Is the value of my interest rate derivative that I want to evaluate. So, and now what I can notice is that this value can be written in this way, just using the equation we have just considered. Now, it is just a matter of substituting the definition of Pt capital T here. And if you go back to the very beginning, we have seen that for us, Pt capital T is what? Is the quantity expectation under QR, which is the measure when we use the money market account as a numeraire of this, of the discounting factor, of the stochastic discounting factor. Okay, if we do that, what we have is exactly what you see on your screen. That is to say, the product of an expectation in terms of QR and the product of an expectation in terms of QT. So we are back exactly to this framework I told you before. And the trick is to introduce the T forward measure and exploiting the properties of the PT capital T process, okay? Now, if we do that, we are in this very nice situation in which we can just write the value of our interest rate derivative instead of the expectation using just the measure QR of this complicated product of dependent terms into the product of two expectations. One expectation takes care of the discounting factor, and this is the expectation with respect to the measure QR, which is the measure in which the numeraire is the money market account, that if you want, in the very simplistic case, can reduce to the risk neutral measure, as we have considered until now. And the second part is just the expectation under the T forward measure. Now, a very simple exercise that I leave to you is if we go back, if you use this setting, so if you just consider this setting here, okay? So if you just consider this equation here that you see on your screen, okay? And you now assume that this quantity RU is just deterministic, you will see that obviously this quantity here becomes just a discounted factor. And this quantity here, it's what? It becomes the expectation under the T forward measure. But the T forward measure, when you assume the interest rate to be constant and to be given and to have no risk, so you are in the risk-free setting, you will see that degenerates. It's not, degenerate is not the proper term. Essentially, is the same stuff as the risk neutral measure we have been playing before. So you see that actually you can still write the expectation of the product as the product of the expectations, but just for the fact that one of the quantities becomes deterministic, comes out, and what remains inside is just this term. for respect, for what concerns the value of the interest rate derivative. So we are in this setting. So you see, these are the two colors we have been using before, and now we are able to split the expectation of the two elements as the product of two expectations. This is extremely important. So please notice that. Now, what we can notice is that the quantity we have been playing before, so this expectation in which we still consider the joint behavior of the discounting factor and the value, can be written in this way. So this is what we have seen and what we have observed before. Before, for example, substituting here the definition of PT capital T. But this is extremely useful because of that. Now, we can substitute to this its definition in terms of the value of the money market account. Okay, so RT over R capital T. Now, if I assume that this quantity here is deterministic, I can take this quantity out. But if this is not the case, I cannot. Okay, so I have to keep it inside my expectation. But what is interesting is this fact, is the fact that I can take this quantity here inside my expectation. So it can enter inside the expectation. Why I can do that? Because remember that this is a conditional expectation with respect to what happens at time t. So at time t, the price in small t of my zero coupon bond with face value €1 or $1 or whatever is known and observed. So it can enter, is not stochastic quantity, it can enter and exit our expectation at time t, okay? So this is what we do. But now this is extremely interesting because remember that P, T, T is equal to 1, okay? And this fact allows me to write the following, okay? So I can start from this. I divide PT capital T by P capital T capital T. So I put this quantity here. And what I get is this equivalence. I have this equivalence with respect between the QR measure and the QT measure of what? Of V capital T, and this ratio RT, R capital T, and PT capital T, P capital T, capital T. Now you may want, okay, but what is that? So we are just playing the three cards. We are always moving the same stuff. In reality, this is a fundamental equation because this is the equation that tells us how we can relate the two measures. This is nothing more than the equation from which we obtain a fundamental quantity for us. That is to say, the Radon-Nikodym derivative that builds the connection between the measure QR and the measure QT. So between our risk-neutral measure or slightly generalized risk-neutral measure and the T forward measure. In fact, what we have is that I can express my Radon-Nikodym derivative in this way. If I see the difference between these, what I see is that this part is the same, this part is really the same. The big difference is in these terms. Now, remember what we did when we introduced the Z quantity that was essentially playing the role of moving us from P to Q, or in general, between two different measures. And then we have seen that in the basic Black-Scholes-Merton framework, this Z is a process, is the exponential martingale, and so on. Now, what we have is that by taking the ratio of these two quantities, we essentially get our Radon-Nikodym derivative, which is expressed as you see here on your screen. Now, it is just a matter of substituting our definition of the ratio RT over R capital T. And for what concerns the denominator, we remember that this quantity here is just equal to 1. So we can get rid of that. If you want, you can keep it, but it's totally useless, it's redundant. So what we have is that our Radon-Nikodym derivative is this quantity, which is a process. Please notice that this is actually a process. And it is a process, why? Because we are assuming this quantity here to be what? This quantity here is a stochastic process, okay? And it enters here and it enters here. Now, one thing that I leave to you to verify is what happens if, once again, you choose to consider a deterministic interest rate or even a constant interest rate. You will see that this Radon-Nikodym derivative becomes something very simple. And why? Because in the setting in which, for example, the interest rates are deterministic, or even better, are constant, there is actually no difference between the two measures. So it makes no particular sense to move from one to the other. So we are essentially playing with the same object. You can choose to call it QR, QT, but it's essentially the same object. What we can read in this result here, and this is very important because we will exploit that. So what we can read in this result here, then I keep on underlining because it's very important, is the following. And I like to underline that for you. To price an interest rate derivative, it is convenient to choose as a numeraire the price of a zero coupon bond with the same maturity, capital T, of the derivative. So when you have to price a given interest rate derivative, it will have a maturity because obviously it will depend on interest over a certain time horizon. What you will use are two measures. One measure, if you want, is R, and it's the part that takes into consideration the discounting factor. And that measure, if you want, mimics, in a more general setting, the risk neutral measure we have been playing before. But for the value itself of the interest rate derivative, we will use another measure, which is the T forward measure, or it can take slightly different names, but let's say that from a epistemological point of view is the T forward measure. And this measure requires us to use as a numeraire what? To use a zero coupon bond that has exactly the maturity of the interest rate derivative we want to evaluate, okay? So you see that by introducing this very basic notation, we can obtain very nice results. Now, in the lecture notes, and we will not cover that with a video because it's extremely simple stuff. And I know that it is already covered in computational finance, and if you are also attending special topics, also in special topics, and in any case, it's very basic things. There is a section which is section 5.2 in the lecture notes, in which we consider some very basic models for interest rates. So we consider the Vasicek model, we consider the Cox, Ingerson-Ross model, we consider affine models, and so on. So I leave that to you. Obviously, if you have questions, you have my email, so you can always ask me. You will see that in this chapter, there are some exercises, in particular 24 and 25 are important. 25 is related with interest rate processes. It's simple, but it allows us to think a little bit about the different processes. We would see that, for example, with interest rates, normality, that in the Black-Scholes framework until now was everywhere because, okay, we had log normally distributed quantities, but it was something that was normally in the logs, okay? So normality was one of the pivotal assumptions, and the normal distribution, a very important ingredient of our set. And you see that also with very basic interest rates models, normality can be substituted by other distributions that I agree at the end of the day are linked to normality, like for example the chi-square that I can obtain by squaring a normal. But it changes, for example, the way in which we are playing with the tails, because the chi-square distribution has another tail behavior with respect to a normal distribution, as also the log normal. But it is important to notice that the set of distributions we can play with is different. There is another thing that I also want to discuss with you, and it will be the topic of our live class at a certain point. So I will be back But one thing that I want you to observe is, once again, spend some minutes. It's not in the lecture notes, so for the moment, I ask you to think about that. We will be back in the live class. Is this equation here, in which we have the generic numeraire. We express the value in small t of our asset in terms of units of the numeraire, okay? And we say that this needs to be a martingale according to a measure that obviously is implicitly defined by the numeraire of the value at maturity of our asset expressed in units of the numeraire. Okay, this is what we have seen before, and obviously, okay, there is the conditionality with respect to the martingale, with respect to the filtration. But what I want you to observe is that actually there is a nice connection between these result and, for example, something that we have said in terms of the Wang transform. So what I want to ask you is try to think about the Wang transform between P and Q, or between D and Q, or between D and P, whatever you want. Or if you want, try to think about the Wang transform in this setting, like, for example, when you assume Vasicek process for what concerns the interest rates, and try to understand a little bit what happens in terms of this transform that distorts one measure into the other. And it's another way of looking at the connection between measures without using the Radon-Nikodym derivative. Okay, so this is something that for the moment I leave to you. We will be back because I think it's interesting to observe a few things. Okay, so that was it. Please read the section 5.2 and study section 5.2. And what we will do next time is to consider the Girsanov theorem. So we will give the general form of the Girsanov theorem. We will see a couple of proofs related to the Girsanov theorem, and then we will see how we can price some very basic derivatives. Depending on the time, we will consider a few of them. But I mean, once you have understood what happens with this system of splitting the expectation into the product of expectations, essentially, you know what is happening with interest rates. And then it becomes more a problem of actual computations, because obviously these objects can be tricky objects, they can be very complicated objects, but from, let's say, an intuition point of view, you're always in this setting, okay? At least at this stage of sophistication of the treatment of financial mathematics. Okay, so see you next time.